So we've looked at 4 different kinds of radiation. There were 5 different kinds of decay, but only 4 of them actually had a specific kind of radiation that they gave off. Electron capture is a way that an isotope decays, but there's not a specific type of radiation that's associated with that. We looked at alpha particles, beta particles, gamma rays, and positrons. And all 4 of these things are going to have slightly different ways that they interact with the world around them. And that's what this slide here is discussing, or at least the portion of this slide that I want to talk about here. So specifically, the ionizing power and the penetrating power of these different kinds of particles. So the ionizing power, as it says here, is the ability to cause damage. So if you get whacked with one of these particles, how much damage will be done? So the alpha particles have the highest ionizing power, and this is mainly because they are the size of a skyscraper compared to the beta particles and gamma rays. They are absolutely ginormous because of their mass compared to these other things. Even if they're going at a much slower speed, they're still going to have much more energy than an electron or a photon would have. So they have by far the highest ionizing power, but then the flip side of that is that it's really easy to protect yourself from them. Alpha particles, you could have a piece of paper between you and the alpha source, and you are going to be essentially safe. When it comes to beta particles, on the other hand, while they don't have as much energy as an alpha particle, again, mainly just because they're tiny, it's just an electron. On the flip side of that, they can actually pass through some matter. They are better at penetrating matter. So you are not safe with just a piece of paper between you and a beta emitter. Some of those beta particles will get absorbed by relatively thin and low density material like that. But a lot of them won't. A lot of them will actually just pass straight through that because they are so high energy and so tiny. They can pass through matter. Gamma rays are just taking that to the next extreme. An individual gamma ray doesn't have nearly as much ionizing power as an alpha particle. Again, just because it's a photon. It's not even a particle in the traditional sense. But it can pass through anything except for lead, essentially. And it had to be, a few millimeters at least worth of lead. Even really thin lead, gamma rays can pass through. You have to have really, really dense material to shield yourself from gamma rays. This is why certain materials that are unstable, certain radioactive materials, are called hard gamma emitters. These are certain materials that disproportionately give off gamma rays versus alpha or beta particles. And those types of materials, you can't even work in the same room with them without being in extraordinary danger. And so if there's some kind of either research being done, or you have some kind of material in a nuclear power plant that is a hard gamma emitter, you actually have a robot that works with the material, and you're in a different room on the other side of the building with a bunch of shielding between you and that material, operating the robot. So gamma rays, even though they, per particle, so to speak, they have the least ionizing power because they are so hard to shield yourself from. They, in some ways, are actually the most dangerous. It just kind of depends on your situation, what you're looking at. For positrons, it's essentially the same as beta particles. Well, not essentially, it is the same as beta particles because they are, again, just the same size and charge as an electron, just positive instead of negative. And when it comes to your DNA molecules getting smacked by something, the DNA doesn't really care if the thing was positive or negatively charged. It's going to get ionized either way. And so it has about the same ionizing and penetrating power as a beta particle. So just depending on which one you are trying to shield yourself from, sometimes if it's mostly just alpha particles coming off of something, you can just wear you know, relatively low density material just as a protective shielding. If you are trying to protect yourself from beta or gamma particles or gamma rays, you're going to need some more intense shielding to deal with those things. All right. This slide here is just kind of a summary, again, of different types of nuclear equations, the changes that happen. This is more just for you to reference back to. There's not really anything new here. All right, so that leads us to this question here. How can we tell if a nucleus, if a particular isotope of an element, is going to be radioactive or not? Is there some way for us to figure that out? And the answer is, unfortunately, there's not really a hard and fast way. There's not a rule that applies every time that you can always tell if something is going to be radioactive or not. But in some ways, the better question shouldn't be, how can we tell if a nucleus is stable? A better question might be, why the heck is any nucleus stable in the first place? Why are we asking ourselves, how can we tell if it's unstable? A better question is, why are they even stable to start with? Because if you think about what's in the nucleus, you have protons and you have neutrons. Neutrons have no charge. Protons have positive charge. In lead, you have 80-something, I believe, protons in the nucleus. How the heck do 80 positive charges stay crammed together in that tiny space when they are, electrostatically speaking, doing their darndest to get away from each other? Because they don't like each other. Like charges repel. So how the heck do these nuclei stay together? Well, I'm glad you asked. The answer is a fundamental force of the universe that you've probably never even heard of before. So all the protons in the nucleus are held together by this force that we very originally call the strong force. The strong force is an interaction between protons and neutrons. So you just thought that the neutrons were just there for show. They are not there just to be there. The neutrons are actually vitally important to the stability of matter. Neutrons are essentially glue, holding the nucleus together. You have all these protons that are trying to get away from each other because like charges repel. But there's this other force that is significantly stronger than the electrostatic force of those protons trying to get away from each other. This strong force that is essentially, again, a glue holding that nucleus together. That's a strong interaction between those protons and the neutrons. This, by the way, is one of the 4 elementary forces in the universe. There are 4 forces that can be used to explain any interaction that you ever come across. There's the strong force, there's the weak force, which I'm not going to get into at this point, partially just because I don't even understand it completely. There is the electrostatic force, or electromagnetic force, which we're very familiar with. We use it to power our everything electronic. It's we're relatively familiar with the electromagnetic forces. And then the 4th one, which you might have thought of as well, that is gravity. That is the 4th force. These are the 4 elementary forces in the universe that can be used to explain anything that happens, scientifically speaking. And the strong force, as the name implies, is by far the strongest of the 4. The strong force is the strongest. I believe electromagnetic is next after that. And I believe that the weak force is stronger than gravity. Gravity is actually an incredibly weak interaction between particles. The reason that we don't really think of it that way is just because, we're used to not, gravity interacting between two particles. We're used to thinking about gravity interacting between you and the entire planet, which is really, really big. But if you think about, the electromagnetic interaction between two ions, you take a sodium plus and another sodium plus, there's a decent amount of force keeping those two apart from each other. There's also gravity that's trying to pull them together, because that's what gravity does. Gravity is always just trying to pull things closer to each other. And it's very clear which one of those wins out. The electromagnetic force will win every time when it's just two little particles like that. Anyway, I'm going off on rabbit trails here. So the strong force is what holds the nucleus together. The strong force is the glue that holds that nucleus together. But eventually, once you get past it's bismuth, I believe, is bismuth is the biggest one, if I remember correctly. Let me double check that real quick. Yeah, so bismuth, which has 83 protons, that is the largest stable element. If you get anything bigger than bismuth, as we'll see later on, there is too much electrostatic force trying to push those protons apart, and no number of neutrons will make it stable. So eventually the strong force is overwhelmed, but it is per particle, it is stronger than the electromagnetic force. Alright, I think we'll call it there for this video. In the next one, we're going to start looking at what we call the valley of stability. These are ratios of protons to neutrons that are stable and ones that are unstable, and we're going to take a look at that. So I will see you all in the next video.